original problem, P can be rewritten as inf sub of L. And now the idea is to say, okay, now consider the interchanged variant. Consider sub inf of L. Okay, consider this problem. Okay, it means the idea is interchange. Yes, idea what happens if the interchange inf and sub. Okay, and now we will prove also the lemma. There is similar to what we did. So we did just before the break, that what comes out is our P star. Yes, what this will be, we will prove it. Yes, to be proven. Our P star. Okay, let us formulate this as a lemma. And actually, this is the derivation of this P star, if you want. Okay, this P star, which was P star, which was maximization of minus B transpose lambda, subject to A transpose lambda equal to minus C lambda larger or equal than 0, is equivalent to supremum over all lambda, infimum over all x, L of x lambda. Okay. Proof, how do we see this? Proof, the idea is again we take this part and give to this part a name. They just call, let's say, d of lambda, the infimum over all x in Rn, L of x lambda. Yes, and I recall what was L, Lagrange functional L of x lambda was C transpose x plus lambda ax minus b. Yes. Okay. Let us now understand what we can say about this d of lambda. Okay, first of all, we rewrite our L. Okay, L was C transpose x plus lambda ax minus b. But you can, of course, rewrite this just looking on the okay, here transpose is missing. Yes, lambda transpose. Just looking for both terms with x together, and you can write this as C plus A transpose lambda times x minus B transpose lambda. Do you agree?
Yeah, sure.
Okay, and now what happens with our d of lambda, which is infimum over all x of this thing? No. Okay, now it's clear what happens. If C plus A transpose lambda is equal to 0, yes, if this is equal to 0, then, okay, then this guy does not depend on x, it's just equal to this, and therefore, also if we take the infimum, what comes out is minus B transpose lambda, yes? And now what happens if they say if this is not the case, if C plus A transpose lambda is not equal to 0, then for sure this infimum will be minus infinity, since, okay, in one component, at least in one component, this is not equal to 0, and then we can, of course, find a sequence of x such that the whole thing will go to minus infinity, infimum is minus infinity, okay? Okay. Therefore, if we look at this problem that we would like to consider supremum over all non-negative lambda of the infimum over all x, L of x lambda. Okay, this is what? This is supremum over all lambdas of d of lambda. Okay, but now if you try to maximize d of lambda, then of course only this case is of relevance since minus infinity is not good for maximization, and therefore this is then equivalent to maximization of minus B transpose lambda subject to this C plus A transpose lambda equal to 0, and okay, of course, lambda larger equal than 0. But this is nothing else but our problem P star. And therefore, this is the description of the problem with P star. Okay, again, in general, what is the idea? The idea is to use Lagrange functional to write the original problem as minimization of maximization of the Lagrange functional, and then to consider here the interchange of inf and sub, and then we get the problem P star. Okay. Okay, now we have formally these two problems, P and P star. And now we will study the relation between these two problems, okay? The first theorem which we would like to study here on the relation between these two problems, this is so-called weak duality theorem. You can imagine if you have weak duality, then later we will have also something which is called strong duality, but let us start with this, the weak duality. Weak duality theory. It says the following. Let X be admissible, X in Rn. In Rn be admissible for the original problem P, and lambda in Rm be admissible for the dual problem, then we have the following inequality, that the C transpose X is larger or equal than mean minus B transpose lambda. Okay, which tells us already that the functional which we maximize in the dual problem is always a lower bound for what we minimize in the original problem. Okay, this is the statement. Let us prove this. Okay, what does it mean? We said X is admissible for P. What does it mean? It means that it fulfills inequality constraints. What does it mean that lambda is admissible for P star? Okay, they have that lambda is non-negative and equality constraints A transpose lambda is equal minus C. Yes, this was this constraint here. Yes, we have here two constraints for the dual problem. Yes, by the way, you see that in the original problem they have inequality constraints only, and in the dual problem to it they have both inequality and equality. Yes, you can also calculate what happens in other cases, but here is the situation. Okay. Okay, this is what we know, and now they just calculate. Just calculate C transpose X. Yes, this is this. Just calculate. What we use that lambda is admissible here, and therefore they can express minus C in this way. And this means C is minus A transpose lambda. Therefore, they have here minus A transpose lambda transposed X. What's that? This is lambda transposed times minus AX. Okay. Now what we have? We have that minus AX is larger or equal than minus B. Yes. AX is less or equal than B, minus AX is larger or equal than minus B. Lambda is non-negative, and therefore if we multiply an inequality with non-negative numbers, then what we get also an inequality larger or equal than minus lambda transposed B. Yes. Okay, but this is the same also then V minus B transposed lambda, of course. And this is exactly what we wanted to prove, that for admissible point x, admissible point lambda, they have this inequality. Okay? Clear so far?
Yeah.
Okay. Now, we have some conclusions from this quite simple theorem. Conclusions. Okay. First conclusion, that if the original problem P is not bounded from below, yes, you remember that in the existence theory they assumed that boundedness from below, it means that there is such an infimum or the admissible set. It means actually that f star is equal to minus infinity. Yes, f star is equal to minus infinity. P star is not bounded from below. Then what we can say about P star? We can say that P star, this P star, does not have any admissible point, since if you take an admissible point, this should give a lower bound for all admissible points here. But if there is no lower bound, if it can go to minus infinity, then it means here there are no admissible points. Yes. This means that P star has no admissible points. Okay. This is one thing. Another thing, also our way around, if P star is a maximization problem, yeah. If this is not bounded from above, then the original problem P has no admissible points. And now the third corollary, the third conclusions, that if they know that both problems, if P and P star have admissible points, then what we know, if, let's say, P star has admissible points, then the original problem is bounded from below. And if the original problem has admissible points, then the dual problem is bounded from above. And this is exactly what we need. What we need to have existence of solutions. Yes, you remember existence of solution was the non-empty, that the admissible set is not empty, and this boundedness from below for the original problem. And therefore, in this case, if we can find at least one admissible point here and one admissible point here, then we can be sure for both problems solutions exist. For both problems, solutions exist. Okay. Okay. This is the third corollary, and then probably okay, very clear corollary C4, but I would like to write it down. I mean, we have this inequality for every admissible point, but for sure, if x bar be a solution, this lambda bar be also a solution, then we still have this inequality. This is clear. Okay, let me write it down. Let x bar is a solution of P and lambda bar solution of P star, then for sure also this inequality holds. This is clear. Okay. Now, these are four consequences, direct consequences. And now, okay, the question will be, of course, if we can say that there is equality here. We'll see in a moment. But first of all, we will say in a moment that if we have equality here, then this x bar and lambda bar are solutions. Let me formulate as a corollary. Corollary from the duality. Corollary is the following. Let x bar in Rn be admissible for the problem P. Again, you remember what does it mean? It means that A x bar less or equal than P. Then let lambda bar in Rm be admissible for P star. What does it mean? It means that lambda bar is non-negative and A transpose lambda bar is equal to minus C. Good. And now let more, okay, we know, of course, in this case that this inequality holds, okay? And let us assume, let moreover C transpose X be equal to minus B transpose lambda bar. Okay. Then, if we have this equality, then X bar is a solution of P and lambda bar is a solution of P star. Okay. This is the corollary telling us again if we have admissible points such that the cost function from the original problem and from the dual problem are equal to each other, there is no gap between them, then we found already solutions. Okay. We'll prove this, and then the next thing, which is called strong duality, will be other way around, that for the solution it must hold this equality. Okay, good. Okay, it's clear what we would like to prove. We would like to prove that if we found admissible point here for the original problem, admissible point for the dual problem, and the values of functionals are equal, then we already found solutions. Okay, this is one of the way also to check if something is already a solution. Yes, you will within an algorithm. Okay. Is it clear what you would like to prove?
Yeah, so basically because of duality theorem, we are guaranteed that C transpose X is greater than or equal to minus P transpose lambda. And for the values of X and lambda where they're equal, we have found solutions for both of the problems, right?
Exactly. This is what we would like to prove. Exactly. Yes. Okay. Okay. What we have, again, what we know, they know X bar is admissible for P. We said already, meaning that AX less equal than B. They know that lambda bar in Rm, yes, here we have N, here M, is admissible for P star, meaning that lambda bar is non-negative and C and A transpose lambda bar is equal to minus C. And now we calculate. Okay, how we calculate? they start with minus B transposed. I'm sorry. Okay, this is of course what we know. This is already written here. Now they take an arbitrary, yes, we would like to prove their solutions, yes. They take an arbitrary, let X be an admissible point for P, okay, just admissible point AX. And the same thing, let lambda be an admissible point for P star. It means that lambda fulfills this, okay? Now what we have to prove? We have to prove that C transpose X bar is less or equal than C transpose X for every such X, and that minus B transposed lambda bar is larger or equal than minus B transposed lambda. Yes, if we have proved this, then we check that X bar is a solution of the original problem, lambda bar is solution of the dual. Yes, this is what we have to prove. Now let us calculate this. We calculate minus B transposed lambda. Okay. We know that this minus B transposed lambda is less or equal than C transposed X bar by weak duality. Yes, weak duality. Weak duality gives us this inequality always between admissible points, and lambda is admissible for dual problem. X bar is admissible for primal problem. We have this inequality. Now, by our assumption, this is equal to minus B transposed lambda bar. Yes. But again, by weak duality, this is less or equal than C transposed X. Again, they have here one admissible point for the dual one and one admissible point for a primal one. Okay. Okay, and here they have all what we want to have. We have
but we still have to prove some things, right? Because we are using assumption, but that is not really a proof, right?
Sorry, say it again.
So we are using assumptions.
Yes, but this is a part of the statement of theorem. Yes.
Oh yeah.
Assumption in this sense, assumption is a part of what we have in theorem. Yes, it's not the theorem saying if this is fulfilled, then this. Okay, and this I called assumption. Yes, this I called our assumption. Okay, if this is fulfilled, then okay, good. And then what we have seen here, they've seen first of all that C transposed X bar is less or equal than C transposed X for all admissible X for P, and therefore X bar is the solution of P. And the second thing we see here, this was okay, this less equal than this. And the second thing we see is this less equal than this. Yes, minus B transposed lambda is less or equal than minus B transposed lambda bar. Okay, therefore this guy again for all admissible lambda for the dual problem. Okay, and therefore, of course, lambda bar is a solution of P star. Okay, good. We are done. We proved what we proved. They proved that if, they have all this inequality. It means in general, not for linear problems, but in general for arbitrary problems, we could have a gap between what comes from the primal and dual problem. Okay. Now they proved that if there is no gap, then they found solutions. And the thing we would like to do now, we would like to this will be a strong duality. We would like to formulate to prove it other way around. We would like to prove that if we have a solution of the original problem, a solution of the dual problem, then there is no gap. Then equality holds. Okay. Therefore, the next goal is to prove if x bar is solution of P. Yes, okay, probably. Let us try to write this down. We know from previous theorem, from this corollary, it was called corollary, yes, from this corollary, we know that if x admissible for P and lambda admissible for P star and C transposed X bar is equal to minus P transposed lambda, then we know X bar is solution of P and lambda bar is solution of P star. This is what we know. And now the next goal is the other way around. The next goal is to prove that X is solution of P. And we know that lambda bar is solution of P star. Then C transposed X bar is equal to minus B transposed lambda bar. Okay, this is what we would like to prove. This is the next goal. Okay, and this will be called strong duality. Okay, good. In order to understand this, we will write down optimality systems for both problems. You will see that there is a reason why we call this guy lambda. This variable lambda in the dual problem will be nothing else but a Lagrange multiplier for the primal problem. You will see this corresponds. Okay. Okay. We start the KKT system for P and P star. Okay, how they look like? Okay, they have a problem P. It was minimize C transposed X subject to AX less or equal than P. And now if you write down the KKT system, you remember the corresponding KKT system, optimality condition, it looks like this. C plus A transposed lambda is equal to 0 and complementarity constraints. AX less or equal than B, lambda non-negative, and AX minus B transposed lambda is equal to 0. Okay. And this lambda is what is Lagrange multiplier? Lagrange multiplier for our inequality constraints. Okay, good. This was the problem P. Now, how does it look for P star? The problem P star, what is P star? P star is the dual problem. It was the problem of maximization of minus B transposed lambda. A transposed lambda equal to minus C, and lambda is larger equal than 0. Of course, this is again a linear problem. It doesn't matter that you have here maximization. If you want, you could rewrite this as minimization of B transposed lambda just, yes. A transposed lambda is equal to minus C and lambda larger equal than 0. Yes, and therefore this is in the general form of our linear optimization problem with inequality constraints and equality constraints. And now how the KKT system, let us call it KKT star, how it will look like. Okay. We will have here Lagrange multiplier for this equality constraints and Lagrange multiplier for inequality constraints. Yes. And we will call X is Lagrange multiplier for A transpose lambda equal to minus C. And the call Z is Lagrange multiplier for inequality constraints lambda larger or equal than 0. And if we do so and just write down our general KKT system, that what comes out is B minus AX minus Z is equal to 0, minus C minus A transpose lambda is equal to 0, and complementarity conditions lambda larger equal than 0, Z larger equal than 0, lambda transpose Z is equal to 0. Okay. This is the KKT star. I recommend you to check this directly, just to look for the general form of the KKT conditions and to see that this is exactly KKT conditions in this case. Okay. Now we can this KKT system, we can write it also a little bit compactor. Just using the fact, okay, here we can always express this Z as B minus AX. Yes, we can always say, okay, this KKT star is equivalent, just using that Z equal to B minus AX, just to, okay, if we throw away Z in this way, then we do not have this anymore. We have just C plus A transpose lambda is equal to 0, lambda larger equal than 0. And now instead of Z larger equal than 0, they have this is larger equal than 0. Or if you want AX minus B less or equal than 0. And lambda transposed AX minus B is equal to 0. And now if you look at this, and if you look at this, then you see no difference. Yes, then you see no difference. In this sense, you see that this KKT here and this KKT star here is the same. Okay, and this is an interesting fact. And now, if we do it very precisely, what we can say from this, we can say the following. We can say that if X bar, lambda bar, Z bar fulfills this KKT star, this system, then just by this logic, this X bar and lambda bar fulfills the original KKT system. And also other way around, if we know that some X bar lambda bar fulfills the original KKT system, then we can say that the triple X bar lambda bar Z bar with Z bar equal to B minus AX bar fulfills KKT star. Okay. In this sense, these two systems are equivalent. Okay. Now they can how they can argue. They can argue very interestingly. They can argue, first of all, statement 1. They can say what happens if we know that X bar is solution of P. Yes, let X bar in Rn be a solution of P. Okay. Then what we know? We know that there exists lambda bar, Lagrange multiplier, such that this pair fulfills KKT conditions. Yes, this our necessary optimality conditions. Yes, there is lambda bar in Rm such that x bar lambda bar fulfills KKT. Good. But now here we know that if some pair fulfills KKT, then this triple fulfills KKT star. Yes. We know that then the triple x bar lambda bar z bar with z bar equal to b minus ax bar fulfills KKT star. And what does it mean? It means that lambda bar is